Okay, hopefully you can see my screen and hopefully you have everything set up on the right-hand side as usual. So let's start with some announcements. Homework 2 was released yesterday. It is due on Monday night. I know the turnaround time is a bit short. You'll have an extra day in the future. We were just a bit behind schedule with homework 1. So homework 2 covers material from this week, meaning Tuesday and today. You can work with a partner if you would like to do so. You can decide that now. There's instructions. This is a new partner workflow, so let's hope it works out. And please keep monitoring Piazza. Speaking of which, posted this poll on morale. So it seems like most of you are doing reasonably well. For those of you who entered low morale, feel free to reach out or come to my office hours. I believe I have an office hour tonight and another one tomorrow morning. Come to TA office hours. We want you to enjoy the course and succeed in the course. And there was a lot of challenges getting set up in this remote environment. So come find us and we'll try to cheer you up. All right, let's get down to business. It's heavy duty stuff today, get ready. So I'm going to load in the Cilantro dataset again that you all generated. As a reminder, we'll be going through a different dataset every week for the first half of the course. And so just to pick up where we left off at the end of Tuesday, we made this plot at the end of Tuesday, which was the accuracy score versus the max depth hyperparameter in the decision tree classifier, which controls how deep is the tree allowed to be, which is the same as saying how many times can it split or how many questions can it ask before it makes a prediction. So we saw a plot kind of like this, and we saw that I'm using the no duplicates data set just so that we can see it actually getting to 100%. But on the real data set from you all, it was capping off around 80-something%. So I just want to show you an upside down version of this plot because that's also pretty popular. So this score here is accuracy, which means when you make a prediction, it's either correct or incorrect. Do you like cilantro or not? And is that actually true or not? Because we know the right answer. But we can also do the fraction incorrect, also known as the error rate. And so here's the exact same plot, just flipped upside down. And now the error going to 0 means you're getting everything right. This upside down version is a bit more convenient and more conventional for what I'm going to talk about today. So you're going to see a lot of these plots with error on the y-axis. But for most of the course, we can probably stick with the accuracy score. Okay, so we talked about this at the very end last class. Why not just always use a very deep decision tree and get 0 error or 100% accuracy? Well, the whole point of what we're doing is to predict on unseen data, and here the score is on the data that has gone into the decision tree. And so great, it does a perfect job of predicting on things where you've already shown it the answer. And so then we talked about the splitting at the end of last class. And so scikit-learn has this train test split function, which splits your data frame in two. And keep in mind that it splits randomly, and that's really important. You need to make sure to split randomly because you could have something weird happening where your original data set is sorted somehow. And if you just took like the top chunk and the bottom chunk, then everything could be totally messed up because you might get all the people that like cilantro at the top and all the ones that don't at the bottom if it was sorted that way. Someone asked in the chat, should we always use random states? So if you call train test split by default like this, then it will do a random split that is different every time, just like generating a random number with a computer. So every time I run this cell, it'll give me a different split. I can show you. So here, this is at the top, 86, 82. I do it again, something else is at the top. I do it again, something else at the top. So the reason for the random state is we just give it some integer. It can be anything you want, it doesn't matter. but that'll just say use this as the seed of the randomness. And so then it'll just be the same every time. And the reason that's convenient is because if you're all following along, running my code, then you'll have exactly the same output as me instead of similar output to me. So it's more convenient for teaching. It's much more convenient for grading your homework if you all have the exact same random splits. In reality, you might want to do this in some cases too, just because you might want it to be the same every time you rerun your code. So that's what this random state does. It's a great question. So yeah, 1, 2, 3 is just something I picked. I just need to pick something so that it's fixed, but there's nothing special about 1, 2, 3 in particular. Okay. Yeah, okay. So getting on past what we did last time, we looked at, or we did look at the scatter plot last time, actually. So this is just the training. Now you can see I'm only using the training portion of the data, and this is just the test part. So wherever you are, if you can find yourself, some of you are now up here and some of you are now down here. And this is called the training set and the test set, and we're going to use the training set to do our fitting, and then we're going to see how well we do on the test set. And that's where we left off last time. So I'm just going to make the X and Y variables for convenience, so I don't have to keep typing in this longer thing every time. And then I'm going to make a decision tree. I'm not setting max depth. So again, by default, that just lets it go as deep as it wants. So you're going to get this very complicated thing. And so we saw this kind of crazy stuff going on last time. Oh no, how did my colors get inverted? Let's see if I can remember what I did. Okay, oh, that still looks bad. Okay, my bad on this. The colors got flipped around, and it's putting red where it should be putting blue, and blue where it should be putting red. I'll have to sort this out after class. But in any case, what we're seeing here, yeah, don't worry about this stuff. It's not important. I'm just trying to get the plot to work, but clearly it's not working. So what I'm showing here is the boundaries of the decision tree. Let me just do one more thing. Sorry to a little bit. Oh, I see. Okay, it's not actually backwards. Okay, so this is the plot of the decision boundary, and I'm putting the training points overlaid on the top. And this is the one that's getting 100% accuracy. And then what I'm doing on the plot below is I'm plotting the same decision boundary. So you can see the background color is the same because the same tree object. But this time I'm overlaying the test data on top. And what you can see here, and why I just confused myself, is that this decision tree is doing a horrible job predicting on the test data. So look, all of these are incorrect. All of these are incorrect. It's kind of like comically incorrect because it learned that there's some blue inside of here, but actually it seems that was just kind of a peculiarity of the training set and doesn't seem to be generalizing to this other data that we held out. And so if we look at the score on the test data, we see actually this isn't a good decision tree at all. It's kind of, sure, it can get 100% accuracy on the data that it's given, but if we hold out some of that data, then we seem to be getting kind of garbage results on some other data. And so this is probably not a good decision tree. So if we look at the scores, we can see we're getting 100% accuracy on the training data and only 50% accuracy, which is pretty bad, actually worse than dummy classifier. So very bad on the test data. And so this phenomenon is called overfitting. It essentially means that we got too specific to the training data. And this overfitting we're seeing here is like really severe overfitting. And the way to combat overfitting, generally speaking, is to use a simpler model. So this decision tree with max depth going as deep as you want can learn these really complicated models. And if we prevent it from getting so complicated, if we say max depth equals 1 or 2 or 3, it's not going to do as well on the training data. But again, remember, we don't actually care about that, and it'll do better on the test data. So there's a question in the chat asking, could this be because of the number of data? And that is an excellent point, and something we're going to need to talk about a lot more. There's kind of an extra element of uncertainty in everything we're doing because of the smallness of the data set, and that's critically important, and we will talk about that more. Okay, so what I'm going to do is I'm going to, let me scroll up for a minute. I'm going to make the same plot as this plot, but I'm going to add another line on it, which is going to be the test error, the error from the test set. So that's this code here. And so here's what we see. We see that same blue line that was there before, that as we make max depth better, the training error is actually going down and down and down. But the testing error, it's actually getting worse. The more complicated the decision tree we're making, it's actually just getting worse and worse and worse every time. And so actually, in this particular case, and as I mentioned last class, I have mild regrets about the cilantro data set because there isn't really that much relationship between how much meat you eat, your grade, and whether or not you like cilantro. So there might not really be much interesting we can do here beyond just dummy classifier and say, well, if the only information we have available to us is how often they eat meat and what they think their grade is going to be, maybe just always predicting they like cilantro is the best thing we can possibly do. However, on the homework this week, the data set you're going to be dealing with, which is the Spotify data set, whether or not people like songs, is a more realistic scenario where you can actually do better than dummy classifier by using a decision tree. Any questions or comments? Okay, moving on. So the error should be kind of the same for training and testing data. So that's what we're going to talk about next. And so we're going to get a little bit technical for the next 15 minutes or so. And bear with me, because what we're going to talk about now is extremely important. It's just more conceptual than most of the things that we tend to talk about in this course. So let's actually, there's some questions showed up in the meantime. So before we start, the error should kind of be the same for the training and testing data. We'll talk about that. Is a decision tree working for categorical data? We will talk about that. I think lecture 6 is called categorical variables. So we'll spend basically a whole lecture talking about that. According to this graph, what should we choose max depth to be? Yeah, so according to this graph, because the thing, test error is kind of the thing we care about more. So if I was trying to pick max depth based on this graph, I would pick it to be super low because the test error seems to be low here. So I'd basically say, you know, I'm going to pick max depth equals 1 or something like that. Modulo the issue that we have a small data set size, which we'll talk about. So I see a raised hand. If you want to unmute yourself, you will be on the recording. So if you're okay with that, you can unmute yourself. Otherwise, you can type into the chat, which will not be on the recording. Can you hear me? Yeah, I can hear you.
Yeah, so I have a question about the error, actually. If your model is wrong more than 50% of the time, and it's a binary answer, can't you just flip to the reverse and get a slightly better score?
Yeah, great question. If your model is wrong more than 50% of the time, can't you just flip to the reverse and get a better score? So yeah, I mean, that would only really happen in extreme cases if you had a... I'm going to mute you. That would only happen in extreme cases. And so, yes, you could do that. That won't really happen realistically. It's happening here in these like laughably bad models, but going into this regime and flipping it is still not going to be as good as being down here, because you're not getting to like 95% error here, you're just getting to 50%. Okay, moving on. So sources of error. This is the conceptual part again. So hang on, this is going to be serious business. So we're going to talk about 3 types of error here. We're going to talk about E-train, which is your training error. That was this blue curve. We're going to talk about E-test. That's your test error. That's this orange curve, your error on your held out data set. And we're going to introduce a new character in the story called E-best, which is the best possible error you could get for a given problem. And so my first question for you is, why is E-best greater than 0? Why can't you get 0 error on any problem? Anyone like to take a shot at that? Okay, someone wrote overfitting. Anyone else? Duplicate data. Too many factors. Randomness. Okay. I really like the randomness answer. So let's dig into this a little bit. So let's think about a data set with no features whatsoever. So all you have is whether you're trying to predict whether or not a person likes cilantro, and you know literally absolutely nothing about them. Well, in that case, all you can really do is predict that they like cilantro, because most people like cilantro. You are given literally 0 information whatsoever. And so that's what you're going to do. You're going to predict that they like cilantro. And so in this case, there is a best error for this problem. And that, whatever that is, if 3/4 of the world like cilantro, the best accuracy you can hope to get on average is 75%, or an error of 25%, because you just don't have any more information. So to kind of generalize that, why is the error not 0? It's because the output, the y, the target variable, is not going to be an exact deterministic function of the input variables. If it was just that, like, you know what, if you eat meat every day, you like cilantro, and otherwise you don't. If that's the way the world was, sure, you could get 100% accuracy, but the world is never like that. And so there could be randomness, and that's why it's non-zero. And it could just be the fact that there's not enough signal, there's not enough information in the features you have to perfectly predict the thing you're trying to predict every single time. And I gave you this extreme case of, well, you just don't have any features, but even if you do have features, they're not going to tell you perfectly exactly everything to always predict it exactly right. And so that's why E-best is not 0. So I see some other stuff in the chat. Yeah, I wouldn't necessarily, you don't have to call them outliers necessarily, but that outliers is one example of why this might happen. But just more generally, I would say the output is not a known fixed function of the input. So you just never really have enough information to perfectly predict every time. I see a raised hand. So again, if you're okay being in the recording, feel free to unmute yourself.
Hi, just a clarification on eBest. So like, is it talking about the highest error or the accuracy? Is it in terms of the training data or the test data?
I'm trying to avoid talking about the specific data set and just saying, what is the best? I'm trying to say, if you were given information about someone's meat consumption and what grade they expected to get in this course, what is the best possible accuracy you could get in general on predicting whether or not they like cilantro? And so I'm not really talking about, I'm definitely not talking about training accuracy, but I'm talking about like generalizing when you don't know the right answer. And so even if you had all the training data in the world, if I asked everyone in the world or millions of people and collected this data, I still am not going to end up with a perfect classifier when it comes to unseen data, because there's just, yeah, some randomness or some factors that are not accounted for in the features. Does that answer your question?
So this value is kind of just arbitrary for the sake of understanding and not actually.
Yeah, it's a conceptual thing. We'll never know what it is, but we need to talk about it in order to do machine learning effectively.
Okay, sounds good. Thank you.
No problem. Okay, there's more stuff in the chat. eBest should always be smaller than eTrain and eTest. We'll talk about that. Excellent question. If we could model something mathematically, then we don't need machine learning. Yeah, sure. So like if the laws of physics determine the relationship between the input and the output, like I put this much force on the spring, how much does it extend? Then yeah, I don't need examples in machine learning if I just kind of know. That's correct. Best means low error rate in general. That's right. So we want to get low error, high accuracy. eBest can be 0. Doesn't that mean there's no need for training? Let's get to that. I'll give you an example of that later. eBest equals the best possible solution. Yeah, it basically means if you had all the data in the world and you could train on it with the best machine learning algorithm ever, you would still not be perfectly good at predicting on unseen examples. There would still be some error left over. Okay, the word error is confusing. So you would still not get 100% accuracy using that model, no matter how good that model was. Is this similar to linear regression where you can't have all the covariates that explain the data? Basically, yes, it's similar to that. Any other questions before we move on? Okay, let's move on. So with dummy classifier, in the case where there are no features, the best you can do is basically that's how well you're going to do, because dummy classifier is not actually looking at the features. So the way you do things in training and in testing, well, you haven't really looked at the training data in this case with no features. And so these are all going to be basically the same thing. What I wanted to point out, and someone raised this issue earlier, is, well, we actually have small amounts of data, so can we even trust anything we're doing? So for example, in this case, dummy classifier gets 63% accuracy on the training data and 75% accuracy on the test data. So first of all, that's kind of weird because the training accuracy is usually better than the test accuracy because we got to see the data. In dummy classifier, we're not really looking at anything, so I kind of would expect them to be the same. So why not better, but why are they so different? And the reason is because we're just, again, we did a random train test split. And so if we did a different random train test split at the beginning, these two numbers would be different from each other. Because again, dummy classifier is not looking at the features. So all it's really doing is predicting, yes, everyone likes cilantro. And so all this is really saying here is that in the training set, 63% of people like cilantro, and in the test set, 75% of people like cilantro, because those are just the training and test set we happen to get with our train test split at the beginning. So all the waters get extra muddied here, and that's why this is so challenging, because we can make these kinds of statements and we can conceptually think about things, but at the end of the day, all our conversation is basically about averages. And in reality, when we look at the numbers, they might not be following those trends. And it really depends how much data you have. So if you have a giant data set, and we'll see some of those in the course, then things kind of behave more as you would expect. And it doesn't really matter that much which train test split you use. But if you have a small data set like the one we have here with only 200 of you, and therefore 200 training examples, it's a pretty small data set. And so if you do train test split again, you might get quite different results. So I wanted to bring that up as sort of an extra major challenge here, that we have to be very careful when we look at any of these numbers. And we'll talk about that more later today about, well, how, can we trust these numbers? See another question in the chat. If we change the split portion on training, can we optimize the e-best? So the best doesn't really have anything to do with the split. It's more of like a conceptual idea, like how hard is this problem? If you're trying to predict whether someone likes cilantro from their grade, then it's just going to be a very hard problem, and e-best is going to be high. If you're going to try to predict whether someone likes cilantro and you're given as a feature whether that person likes cilantro, well, sure, then e-best will be 0 because you're just given the answer. So it's really a function of how hard the problem is. Yes, exactly right. So because more than 50% of people like cilantro, dummy classifier picks yes every time. That's exactly right. That's what it does. Okay. So let me move on here. Actually, I'm going to skip this case in the interest of time, that you can take a look over it later. And I just want to go straight to our actual cilantro data set. So in the case of the cilantro data set, let's assume there's actually some information here that maybe people who, just speculating, maybe people who like cilantro have a better time with vegetables, and so they were more likely to become vegetarian. And so maybe there's a slight relationship between people who eat meat more often are maybe less likely to like cilantro. So if that relationship exists, we can start lowering e-best. We can actually start to do better by learning from the data. And so you can think about that as there is more signal, or there's more information about the target, the thing we're trying to predict, contained inside the features, which is the things we have in order to make the prediction. And so as the features become more and more rich and more informative about the target, the best we can do on a given problem gets better and better. But as I was saying before, e-best will not really go to 0, because in any real problem, you just can't exactly know what the target is going to be just given some features. And so basically in a real problem, you should never expect to get 100% test accuracy or 0% test error. That's just not going to happen in any real data set. And it's because there's this this bar, this best you can possibly do, and you can't do any better. And the frustrating part is you don't know where that line is. And that's one thing that makes this so hard. So when you solve a problem and you say, hey, I got 90% accuracy, you kind of have no way of knowing if you should keep trying to do better, or if 90% is actually the best any machine learning algorithm could do. And that's just something we have to struggle with. Okay. So let me talk about some important terms in machine learning called overfitting and underfitting. So a very common scenario you're going to be in is this one here. And we saw that earlier. So if we make a crazy deep decision tree, we can basically make E-train 0. We can get perfectly label every training example by doing this crazy, lots and lots of splits. And so you can get E-train to be very small or 0. And E-test is typically going to be worse. And in the scenario we saw earlier today, it was a lot worse. It was performing horribly on the test set. And the best is typically going to be somewhere in between there. And so, if e-test equaled e-best, that would be like amazing. You're achieving that best thing, but usually you're not achieving that best thing. And with more effort, you could do a little bit better. So this is kind of a common ordering that you'll encounter. And it's called the overfitting scenario. And it's called overfitting because the training error is less than the test error. So you're overly fitting things to your training data set, doing really well in the training data set, but that's not translating into generalizing on the test data set, and so your test error is higher. So that's kind of scenario number one that you will often find yourself in, and you're going to start seeing that even in the homework, but you're going to see that throughout the whole course. And the other scenario is called underfitting. And underfitting, so overfitting happens usually when you have a really complicated model, like we just talked about, a tree that splits and splits and splits and gives us those crazy looking pictures. The underfitting scenario is kind of the opposite of that when you have an extremely simple model. So dummy classifier is basically the simplest thing we're talking about here. It doesn't really do anything. It just predicts the most popular class. Or decision tree with depth 1 is very simple. So in that case, you're probably not going to get overfitting. So with dummy classifier, for example, in general, you're going to expect the train and test to perform about the same, because fit with dummy classifier is not really doing anything. It doesn't really learn any weird boundaries specific to the training set. It just finds the most popular class and predicts that. And so on average, you're going to get that same proportion of yeses in the train and test set, and these will be about the same. So with this squiggly, I'm saying they're usually about the same, but maybe training is slightly less. But you're not going to be as good as eBest because your model is too simple. And had you made your model much simpler, you might have been able to get better and get closer to that eBest where we're really trying to get, even though we don't know where it is. And so these are two very important terms. Again, overfitting, where you have a very complicated classifier, and underfitting, where you have a very simple classifier. And we're going to be talking about these over and over again. Questions in the chat. So if we see a train error reaching 0, should we stop training? Awesome question. If you see a training error reaching 0, that's not enough information to make a call in itself. You should also look at the test error, or something called cross-validation error that we'll talk about later today. If you see the training error reaching 0, but your test error is really big, then that's a sign that you're overfitting and you might want to use a simpler model. If both the training error and the test error are really high, they're both doing a bad job, that's a sign you might be underfitting and you want to use a more complicated model. So I see another question. When we score a tree, should the score for the test data set be lower than the score for the trained data set? In general, yes. Except for the randomness of the fact that we have maybe small data sets, that's generally true, that the score will be lower for the test data set. Another question, e-test minus e-train is smaller is better. We'll get to that in a second, so just hold on to that. In an underfitting scenario, can e-test be smaller than e-train? It shouldn't be conceptually, but it might be because, again, there's some randomness here in our train test splitting. So you could observe that, but it wouldn't tend to be that on average. Are there bounds for high and low, like a 60% bad? Beautiful question. The short answer is no. You can't say if 60% is good or bad. And so that's why I keep telling you, start with dummy classifier, because that will give you some bearings for the problem you're working on. If you start with dummy classifier and you get 90% accuracy with that, then sure, 60% is horrible. You should be doing better than 90%. And so it really depends on the problem. Another question, just to clarify, e-train is not necessarily equal to the score on the training data. Sure, I'm talking about e-train as a bit more of like a conceptual thing. But when you actually score it on your particular training set, there's this kind of extra randomness factor. So I guess it depends if you want to define e-train as like a specific number on your exact training set, or this kind of conceptual thing on some training set. And I guess I'm fine just being a bit vague about that as long as we know what we're talking about. So let me keep going here. Thank you for all the questions. Okay, so a standard, I think we already talked about this, but a standard question to ask yourself is, which of these scenarios am I in? So you're working on a problem, well, how can you figure this out? Am I overfitting or am I underfitting? And so you can never see e-best, but you can see your training and test error, at least for your particular data set. And so I think we talked about this a little bit, but yeah, if your training error is 0 and your test error is huge, you're probably overfitting. if they're very close together, you're not overfitting and you might be underfitting. And so going back to this plot we looked at earlier, here we can see super obvious overfitting. When the depth is huge, we have basically zero training error and huge testing error, which is like the classic overfitting scenario. And this data set is not very good for showing underfitting. So let me talk about the homework 2 data set for a minute. So this is the cilantro data set. Again, there's just not a lot of signal in it, so we can't really see something that I want to show you. So here's a plot that you're going to get. You're going to get something like this plot in homework 2 for the Spotify data set. Sorry for flipping the axes on you. This is back to accuracy here because I just screenshotted it from the homework. So this is like a very classic situation that you're going to see on homework 2, which is that you get a deeper tree, the training accuracy just gets better and better and better and better, and it reaches 100%. But look at the orange curve here. This is very interesting because as we get the tree deeper and deeper, things get worse and worse and worse, which is kind of what I talked about, overfitting. You're having this crazy, overly specific tree being learned that actually is only relevant to your particular training set and is not good at generalizing. But here, it does actually get better first. So the test error does actually get better first, which means having a tree of depth 4 or 5 is better than having a tree of depth 1. So if we go to this bottom left corner here, that would be the underfitting scenario, where your model is so simple, it's a tree of depth 1, that your train and test accuracy are about the same, and they're both pretty bad. And by increasing the depth, you can make both of them better. And so here you haven't really started overfitting yet. You're just starting to get rid of the underfitting, and things sort of get to the sweet spot, and then you start overfitting. And so that's kind of how to read these plots, and is really important. Any questions about that? Okay, so now we're going to talk about this fundamental trade-off, and which is basically what we looked at in this plot, which says that as you increase model complexity, so for example, a deeper tree, and we'll see many other examples throughout the course of different models and how to make them more or less complex, the training error tends to go down. So more complex model, you tend to get better job on the training set, because as you get more complex, you can just fit the training set in more detail and bring down that error lower and lower, for example, by having a deeper decision tree. But this difference of test minus train, this gap tends to go up. And so if you look here and you think about the gap between the two lines, you can see that keeps going up. And so that's basically this fundamental trade-off, which is that should we use complex models or should we use simple models? Well, there's a trade-off, because making it more complex makes you do better on training, but makes this gap bigger. And so at some point, there's often this sweet spot in the middle where the gap is kind of medium-sized, but the training accuracy is pretty good, and so the test accuracy ends up pretty good. So here the gap is small, but the training accuracy is also bad, and so it's not worth having such a small gap. Here the training accuracy is amazing, but the gap is huge, and so that's not very good either. And here you get this kind of thing in the middle, this peak coming from this fundamental trade-off. So it's kind of the trade-off between underfitting and overfitting, and going too extreme in either side is bad. And part of our jobs is to figure out the sweet spot in the middle, which we'll be talking a lot more about. Okay, so if you've heard of the bias variance trade-off in statistics, it's a similar kind of idea. So yeah, very simple model, underfitting, you're not really fitting, you're doing too little. You could squeeze more out of the data with a more complex model. Very complex model, overfitting, you're getting way too crazy with the training set, and it's not actually useful for anything, and it actually does really badly on unseen data. I won't really get into the bias variance thing. I just wanted to reference it if you've seen that before from statistics. Why do we worry about the gap if we have a scenario where the test set is also improving? Okay, that's a great question. So I wouldn't say you really have to worry about the gap. I mean, you could just say, who cares about this trade-off? I'm just going to try and get the best test accuracy and not think about anything else. And that's kind of an okay, like, beginner's approach to this. But then as we get more nuanced, as we will throughout the course, it becomes useful to think about this bigger picture. So yeah, I think at the beginning, we can just say, you know what, I only care about this orange curve. I care about unseen data. The orange curve is for unseen data. I'm just going to find the best one and leave it at that. But there will be times where this conceptual framework is extremely useful for us to be thinking about this trade-off in terms of model complexity. It's a very good point, though. Okay. I'm just kind of laughing at myself because in my notes from last year, I said, this should be split into 2 lectures. And then I looked at it this year and I said, yeah, I don't know what I was thinking, but now I know what I was thinking. In any case, I think we need to take our break now because it's already 11:42. So let's take our break now and we'll resume at 11:47. Next thing I want to talk about is some terminology. So going back to the test set, what is the purpose of the test set? The purpose of the test set is to assess how well we're doing. Because looking at the training accuracy or training error is not really of interest to us. What we want to know is how well we do on unseen data. And so we talked about tuning hyperparameters, like max depth is really the only hyperparameter we've seen so far, but we're going to talk about a lot more throughout the course. So how do you pick max depth? And so far, what I've been doing, and I won't do this anymore, I was only doing it for today. So far, I was using the test set, but we don't actually want to use the test set for this. And the reason is a bit subtle, but remember the whole point of the test set is that it's supposed to be unseen data and give you kind of a fresh estimate of how well your model does on data it's never seen before. But if you use the test set to pick max depth and pick 10 other hyperparameters, even though it's not seen by fit, you're not directly passing it into fit, you're still using it to do a bunch of experiments and decide what is best. And so the end model that you end up with does in some way depend on it, just in a more indirect and not so obvious relationship. But somehow to get to where you ended up, you did use that test set. And so you can't truly call it unseen data anymore. It's kind of been contaminated. And so we need to avoid that. If we really want a good assessment, we want really unseen data that we have literally not touched in any way this whole time. We just want to split it off at the beginning and not touch it. And so what we might actually want to do is split our data into 3. Train set, validation set, and test set. And that's why I had that axis, that legend valid before those for validation. So if we split into 3, well, the disadvantage of that is now we have less data to work with in each case, but I'm just going to go ahead and make some recommendations in this course, including doing things in the way I'm about to describe. So if we do it this way, we can use the validation data for model tuning. Someone asked, what is a hyperparameter? It's something that we talked about at the end of last class. That it's basically the thing that the human selects before you start fitting. So the one we've seen so far is max depth on the decision tree, but we'll see many more. And so what we're going to do is we're going to use the validation data for all kinds of experiments when we need some unseen data to mess around with to see how we're doing, like trying out different values of max depth. But we still keep a separate uncontaminated test set for the very end, just to kind of feel better about things. And this is especially important when you're using the validation set a lot. So if you're trying a million different values of the hyperparameters, then you've kind of contaminated or compromised that validation set more. And that's when this becomes especially important. So someone's asking, what's validation data? So I'm now introducing a third split of your data. I'm saying, instead of splitting it into 2, splitting into 3. And so validation data is just another chunk of your original data set now. So there's some terminology we're going to use in this course. People use tests and validation to mean different things. We're going to use them in a specific way. So in the course, validation and test data are both splits off your original data set, where you have access to the right answer, but we're going to use validation data for model validation and hyperparameter tuning and all kinds of experiments, whatever we feel like doing. We're going to talk about a whole bunch of things throughout the course. We're not going to pass them into fit. We're not going to train on them. That's what the training data is for. But we're just going to keep this test data set locked away until the very end to say, hey, this is really unseen data. I have not touched this data in any way, as a kind of best practice for doing that final assessment at the end. And then I'm going to introduce a new term called deployment data, which is a term I made up, which is the final case where you actually want to use or deploy machine learning. Like, why are we doing this even to begin with? We're doing it to deploy it. So in your homework, you're going to look at the Spotify data set. You'll get some features or attributes about a song and try to predict if someone likes the song. And so you actually want to deploy that by taking a new song and predicting if someone likes it without actually knowing the answer. That's like the real case where you're using the trained model finally to actually do something, to predict a user's behavior, or whether they like the song or whatever it is that you're trying to predict. That I'm going to call the deployment phase. And so the deployment data, there is an X, which is some new user and what kind of songs they like or whatever. But we do not have the Y, because the Y is the thing we're trying to get. The whole reason we're doing all of this is so when we put something to deployment, we can predict what the Y is going to be. So that's what I'm going to use about deployment. Yeah, really great question. If we have a small data set, how does this three-way split work? So if you don't have a lot of data, it is a concern, but we're just going to roll with it. And the next thing I'm going to talk about is going to help with that problem a little bit. How is deployment data different from test set? Test set is part of your original data set where you know the answer, you have the Y values, and you're saving it for assessment. Deployment is when you're actually going to use this later on, and you don't know what the Y value is, because that's the whole reason you're using this. Someone's asking how we should split. So we'll talk about that in a minute. But you could use, for example, people use something like 20% for test or something like that. And I'll talk a little bit about how much you use for validation. Okay, so I made this sort of table for you to keep track of these different data sets. So the trained data, you can do whatever you want with it. The validation data is not being passed into fit. You can compute score on it, which you're going to do if you're testing out different hyperparameter values. And that means you can use predict, because remember, score actually calls predict. Score just makes a prediction and then checks if it's right or wrong. So those are basically the same. The test data, you can do that, but you only do it once at the very end. The deployment data, you cannot call score because you need the right answers in order to find out a score, and you don't have the right answers. That's what deployment phase is. And so the only thing you're ever doing is calling predict on the X values in deployment and getting out a prediction, and then you're going to use it for something, because that's why we're doing it in the first place. So just a sort of a reminder, so these splits are kind of like you're taking the first, this many for train, you're taking this many for validation, and you're taking this many for test. So you're splitting by rows. I just want to confirm, not by columns. It's the examples that we're splitting. Okay, so again, let me move past this, because we really need to talk about cross-validation for your homework, and the rest of the stuff I can deal with after the fact. So yes, my bad on the timing, but let's talk about cross-validation. So what I just described, splitting into three, is not actually what we're going to do most of the time in this course. It's a way of thinking. And you've already asked in the chat, hey, I don't have that much data. Do I really want to split it into three? And that's exactly the problem we're going to address here with cross-validation. So if your data set's small, if you don't have that much data, you kind of want to make the most of it. And so by just taking some for train and some for validation, Well, whatever you have for validation, you can't use for train, and whatever you have for train, you can't use for validation. And so cross-validation is kind of a trick to squeeze the most out of your limited amount of data. And here's how it's going to work. So cross-validation, it's sometimes called k-fold cross-validation because there's this number k that you get to pick. That's a parameter, as you'll see in a minute. And so this diagram shows a 5-fold cross-validation. So here's how it's going to work. You have your data set. And so think about these are like, think about you have 200 cases in our Cilantro data set because there's 200 of you. And so we're going to chop it into 5. So 40 of you are going to be in fold 1, 40 of you are going to be in fold 2, 40, 40, 40, and that'll make up the 200 of you. And so now we've divided all of you into 5 folds. So here's what we're going to do. For each fold, so let's start with fold 1, where again, that's just 40 of you. Actually, it's not quite 40 of you, I should say. First, we did a train test split. So maybe we took, I don't know, 50 of you for a test, and those are now locked away, and we have 150 of you left in our train. And now we divide that into 5. So it's actually 30, 30, 30, 30, 30, I should say more accurately. And so here's what we're going to do. For the first 30 of you, we're going to do this train validation split where the first 30 of you are going to be the validation set. So we're going to train on the other 120 of you and test the model on those 30 of you. And so it's kind of like we did a train validation split with 120 of you for train, 30 of you for validation, and we're going to compute an accuracy score or an error, and we're going to write that down. So say 0.34, for example. So that was just like a regular train validation split that we just talked about. But now we're going to take the next 30 of you and say, okay, hey, next 30 of you, now it's your turn to be the validation set. And so now another different 30 of you are the validation set, and I'm training on everyone else and validating on that 30 of you. And I get a different score, say it's 0.41. And then I go to the third fold, which is the next 30 of you. And now it's your turn to be the validation set, train on everyone else, get the score on you, write down the score. And then in the end, I have 5 scores where each score comes from a different 30 of you being the validation set and the other 120 of you being the training set. And then I'm going to average these numbers together to get an overall average score or error, in this case, 0.34. Yeah, is the red 20% part the 30 students and the blue, the rest is 120? That's correct. I thought each fold wasn't equal to 150 people. So each fold is a division of the 150 into 120 train and 30 validation. Am I using the words validation and test interchangeably here? No, not at all. So the test set, as we just talked about, is being kept separately for our final assessment. And now I'm just talking about train and validation. Does every fold include all the students? Yes. So for every fold, every fold includes all the students that are not on the test set, which we took 50 of you students right away at the beginning as our test set to say, we're not going to look at those 50 students until the very end for our final test assessment. And so you 50 are kept separately. But for the other 150, yes, each fold is splitting you into 120 for train, 30 for validation. So in other words, yes, each of these folds is within just the training part, because the test part we've separated off right at the beginning. Okay, there's not a lot of love for this figure here. Can you draw us another one that includes a test set in different category? Okay, I can do that. Not at this exact moment, but I will do that. Does that mean each person is the red part once? Yes, that's exactly right. Okay, so this approach helps us basically get more out of our training data, because we've kind of cheated and reused the data 5 times by doing a different train validation split 5 times. And so we end up getting a better estimate of how well we're doing for what we're trying to try out, like our particular hyperparameters. Someone says, basically you put test aside, then take the training set and further split it into train and validation set. That's exactly right. Okay. So let me show you this in the code. So with scikit-learn, there's something called cross-val score. And so we can import that. And we can make a decision tree classifier. And let's say we're trying to test out, is max depth equal 1 a good hyperparameter? We want to get some kind of score on it to see if it's a good hyperparameter. But we're not going to try that out on our test set because we don't want to contaminate our test set. We want to leave it untouched until the very, very end. And so what we want to do is do a train validation split because we still want unseen data, which is the validation data, but we don't want to touch the test set until the very end. And so with scikit-learn, we can do cross-val score. Here I'm setting CV equals 10. That means do 10 folds. Above we have 5 folds. I could do 5 for now as well. So what it's doing here is giving me 5 scores, which are basically these 5 numbers. And so what it's doing under the hood is taking my training data, again, say 120 of you, and then here the first 30 of you, say 150 of you. The first 30 of you are used for validation, the rest for training. The next 30 of you are used for validation, the rest for training. The next 30 of you are used for validation, the rest for training. And each time I'm getting a score. And then I can take the mean or the average of these scores, which is 0.65, and I get something more robust or more trustworthy than if I only did one split. So it's getting a more reliable estimate of how well I'm doing by using the same amount of data, by kind of using our data in this clever way of just re-splitting it over and over again. And yeah, you can change the number of folds. So the default is 5, but you can change it to 10. You can change it to 20. And normally the disadvantage of using lots of folds is it just takes a long time. In this case, our data set's so small that nothing's taking a long time. But normally that's a concern. So another thing which I ask you to do in the homework is that you can actually look at these numbers and say, well, hey, are these numbers kind of close to each other? Because if, for example, all the numbers were exactly 0.612 something, then I'm feeling pretty confident 0.612 is probably a reasonable score. But right now, these numbers are ranging quite a lot from 0.57 to 0.85. So there's kind of a massive variation in these different scores. And the reason for that is because the data set is small. And so as I was saying earlier, randomness is just a huge factor here that's making our lives more difficult in every way when we have smaller data. And so it's nice to, people typically average the numbers, but it's nice to actually look at the numbers and say, well, hey, how much are these varying? Because that kind of gives you a sense of trust. Because it's basically saying, well, if I had split it one way, I'm getting 86%. And if I'm splitting it another way, I'm getting 57%. But it shouldn't really matter how I split it. That's just kind of a random thing in my code. And so you might want to say here that the accuracy is around 0.65, but with kind of big error bars and not super trustworthy. So as something, kind of a habit I'm going to try to build in the course is to take a look at these numbers, to just do a reality check with ourselves. And as you'll see, the more data you have, the more close together these numbers will be. Why not choose the average score? No, we do choose the average score, just to clarify. We take the mean. Another question, if our data set is big enough, would using cross-validation make the model more robust? So cross-validation doesn't change the model. It's purely a method of assessing how well we're doing. If we can assess how well we're doing accurately, we can end up with a better model because we can pick good hyperparameters. So it's good to be able to assess how well you're doing when making decisions. But cross-validation isn't a model building technique, it's a model assessment technique. Why not choose the highest score? Well, I mean, you're trying to get an honest assessment of how well you're doing. Just picking a highest score and telling it to your boss is kind of misleading. And the whole point of doing this is that you honestly want to know how well you're doing. And so if you split the data 10 different times, then taking the average just gives you the best guess of how well you're actually doing. And so taking the highest one is also more random, because this can vary a lot more, what the highest one will be, and the average is a more robust measure of how you're actually doing. Okay, so a quick note on cross-val score, the scikit-learn function. It doesn't shuffle the data because train test split already shuffles the data. And so cross-val score actually doesn't shuffle the data. It assumes it's been pre-shuffled by train test split. But you might still get different results if you run it again and again. So here, I think if I run it again and again, I'm getting the exact same results. But you might get different results sometimes if the model itself has some randomness. So that's just something to watch out for. Is that sometimes the model itself has randomness, like decision tree classifier. If there's a tie, it might break ties randomly and that kind of thing. So a sort of general framework here is that if you're trying to pick between, should I use hyperparameter number 1 or hyperparameter number 2, you can try different values of hyperparameters, like max depth equals 1, max depth equals 2. And for each one, you can, and for each one, you can try it out. And cross-val score is basically going to give you an assessment of, well, how good is that? And then when you're done, you can pick the best one. And so under the hood here, there's kind of an inner loop that's looping over those 5 folds, or however many folds you have. But cross-val score is taking care of that inner loop for you, so you don't really need to worry about it. Okay, I see there's some questions, but I just want to talk about this one more scikit-learn function in the last 3 minutes, which is cross-validate, which is kind of the same thing as cross-val score, but it's just a little more powerful. It has a little more options, and it's useful to use. So it returns this horrible mess that's actually a Python dictionary. But if you cast it into a pandas data frame, it's a lot easier to read. So cross-validate, this final column is basically what we were looking at before. It's giving you 10 scores, doing the exact same thing as cross-val score. But it's giving you some extra information. In particular, it's actually timing the number of seconds it took to do these different steps, which is not super of interest to us right now. But what is of interest is that you can also ask it to return the training score. So if you set return train score to true, then you get this extra column. And this is kind of nice because it's generally good to I often want to know what is and unfortunately scikit-learn calls this test score, but it should really be called cross-validation score. Kind of frustratingly, they called it test score. So often I want to know both of these things. I want to know how good is my validation score and what is my training error, for the reasons we talked about earlier about the fundamental trade-off and overfitting. It's an informative diagnostic to be able to see the training score. So I kind of like to do it this way, unless it makes the code too slow, which is the reason it's not the default. It makes the code a little slower to compute these things. So if that's an issue, then this is good to do, and the homework has you doing this as well. So going back to the plot we've been making, that we've been looking at with the Cilantro data set and the depth of the decision tree, the plot that I would really like us to be making from now on, and that will be the last time in the course where I had train versus test and a hyperparameter changing on the x-axis. What I really want us to be doing is having a cross-validation score that we're looking at, and not touching the test set until the very end. And so here I'm just calling the cross-validate function, and then I'm pulling the training score and the test score out of it and computing the averages of those things. and the rest of the plotting code is basically the same. So in general, a kind of thing we're going to do over and over and over again in this course is we're going to start out, we're going to immediately split our data set into train and test. So the test data set is completely unseen. We're not going to be messing with it because we want to have some truly untouched data set for the end to do an assessment. We're going to use cross-validation on the training split to do our model validation, hyperparameter tuning, whatever experiments we want to do when we're doing our machine learning. And then at the very end, we're going to try things out on the test data to see how well we're doing. We are out of time. Someone asked where we can find the recorded lecture. Yes, it's on Canvas. It's also on the GitHub page. I think I've talked about everything you need for the homework. I apologize for the rush today. I should have listened to my past self. And let's wrap it up here so we don't go over time.
Hi, actually, I had one quick question. Is that okay?